Okay, so the last talk of this session, it's practical pre-match attacks on 3-round Ketchak 256 and 4-round Ketchak R equals 640, C equals 160. And the talk is given by Xiaowen Lin. Thank you very much.
Thank you for your introduction. Hello, I'm Lin Xiaoen from Tsinghua University. Today I will introduce the paper. Oh, sorry. Wait. My presentation mainly includes the following parts: the research problem, related work, our attacks on the two instances of Ketchak, and the conclusion. Hash function is a vital cryptographic primitive. It processes an arbitrary length message into a fixed size digest. It requires critical properties like pre-image resistance and collision resistance. For pre-image resistance, given a digest, find any message whose hashed result matches the digest should be computationally infeasible. This paper focuses on pre-image cryptanalysis on round-reduced Ketchak. Ketchak, which is chosen as secure hash algorithm standard, is an important hash function. It uses the sponge construction where the Ketchak F permutation operates on a state of B bits. And it consists of several rounds, where the round function has these 5 steps. These are the relations of the main related work. In the following, we will review these works, which are related to our attacks. First, linear structure. Suppose we have some free variables, and every bit of a state can be represented by these variables. Then we use some different colors to denote the different situations. For a state, the bits on the same lane usually perform similar. And we consider a lane-level state representation with phi times phi squares. When the state is operated by the round function, we add some equations to control the column sums and prevent the diffusion of the variables. Then the state stays linear after 2.5 rounds. There remains 64 degrees of freedom, which can be used to match the output digest. Next, allocating approach. There is an improved linear structure with more degrees of freedom. However, it requires that some bit pairs of the starting set should be opposite, or else every unsatisfied bit pair will cause some quadratic bits, and require adding an extra restriction to eliminate the effect. Thus, the attack can be divided into 2 stages, where the first stage tries to produce a state with as many bit pairs as possible, and the second stage deals with the unsatisfied bit pairs and use the rest degrees of freedom to match the output digest. Then, iterating and FIFO3 strategy. According to the linear structure, a starting state with more opposite bit pairs will have more degrees of freedom, restricting the starting state of the next block. So a better starting state is more likely to be generated. Therefore, the first stage can be extended to multi-blocks, and the state will be improved iteratively until a good enough one is obtained. Besides, with these 5 restrictions, 3 opposite bit pairs can be controlled using 5 degrees of freedom with high efficiency. Thus, quadratic structure and relinearization technique. When a quadratic equation system is overdetermined and the number of quadratic terms is relatively small, then the equation system can be linearly solved by relinearization technique, which is a special case of the crossbred algorithm. This is an example. By replacing the quadratic terms with new variables, the quadratic equation system becomes linear, and the variable can be solved by Gaussian elimination. We then check whether the value of the new variables match the replaced quadratic terms. When applied to linear structure, designing a quadratic structure with relinearization technique may bring better attacks. So how to make further improvements? We are now facing two difficulties. The first one is that within acceptable complexity, we can only obtain a starting set with still around 8 unsatisfied restrictions. The second one is that even if we could obtain a state satisfying all the restrictions, the number of degrees of freedom is still not enough for digest matching because more than 60 restrictions should be matched randomly. We should find a way solving these two difficulties at the same time. To address the second difficulty, the most direct way is adding variables. Although some quadratic terms will appear, there are over 60 linear equations not considered in the digest matching. So the quadratic equation system can be linearly solved using relinearization technique. Thus, we are now focused on how to add as many variables as possible while the number of produced quadratic terms is limited according to the number of redundant linear equations. To produce fewer quadratic terms, the best way is adding variables on the second sheet, because every added variable will produce only 4 more quadratic terms, which means we have around 13 more degrees of freedom that can be used in digest matching. On the other hand, we are hopeful that these changes can also address the first difficulty at the same time. Fortunately, such a solution does exist. To match the starting state, the key is ensuring appropriate B-pair relations so that when the fifth plane is matched, the fourth plane can be matched simultaneously. Therefore, we need that these 6 lanes should be appropriate constants. After row and pile operation, these 6 lanes on the state before the Chi operation should be constants. We then consider the property of the Chi operation. For a certain row, there are 4 optional setups. The first setup is the only case that the 5th bit is constant. So these 3 planes must belong to the first type. But for the third plane, rows can belong to any type. The only requirement is that, due to the limitation of the redundant linear equations, we can only add 13 more variables. Thus, for the third plane, the number of the rows that belong to the third type and the fourth type should be less than 13, which means at most 13 bits on this lane can be 1 rather than 0. When it is reflected in the starting state, bit pair relations on the third lane and the fourth lanes should be opposite. However, at most 13 bit pairs relation on the fifth length could be same. So we introduce a middle stage linking the first stage and the third stage. These are the equations we added. It has high probability satisfying the third and the fourth bit pairs, while the fifth bit pair also shows a promising probability. To satisfy the uncontrolled restrictions randomly, we need to guess different values for some bits and repeat the attacks for many times. Here we point out that choosing different variables to guess will result in different solving time. In previous work, they guessed different values for the colon sums. However, if we guess values for these bits, the equation system that we need to solve will be very simple. Let's look at these 2 examples of equation system. Which one is more friendly to solve? It is obvious. Although the 2 equation system over X will both become linear when we guess all the constants, A or B, the right one is much easier than the left one to solve. First of all, some equations on the right have already been linear and will not change between different guesses. Besides, by guessing every one constant, many equations on the right will become linear. However, if we hope to linearize an equation on the left, it requires guessing almost all constants. Also, on the left equation system, there are quadratic terms over A, while the right equation system remains free. As a result, although the number of guessing times are the same, the complexity of solving time can be much different. By guessing bits on theta 1, 4z of the second round, we just need to deal with only around 10 linear equations on average for each guess, resulting better solving time. Next, we will introduce the pre-match attacks. on 4-round Kerchak are equals to 640 and C equals to 160, which is an instance of Kerchak crunchy contest. The previous work is using quadratic structure solving quadratic equation systems. To make further improvements, we use several techniques. First, recall the variable selection of the linear structure. There are two benefits. One is that after the first chi operation, the variables bits will only be in two sheets before the theta operation of the second round. The other is that the bit-pair relation contributes to matching the starting set. However, the second benefit is no work for this Kerchak variant because the capacity part only involves the last plane, and the bit-pair relation cannot bring many extra gains. Thus, we may adjust the selection of variables so that the linearization can be easier for the specific required object. Second, consider the matching of the starting state. We select two candidates for the previous message block so that one more degree of freedom can be saved. Here is an example. Suppose we have a 16-bit capacity. We can add 15 linear equations so that 16 bits are restricted among these two options. Note that if we extend to more candidates, the number of degree of freedom will be increased, while the probability of matching will decrease, which is noteworthy in this attack. Third, for linearization of the last two rounds, we optimize the constant settings of the column sums. So that more bits before the start theta can be constant and the linearization can be easier using zero coefficient technique. Also, we carefully select the Gauss constant bits, which are used to simplify the quadratic equation systems so that they contribute to linearize more bits at the same time. For digest matching, we consider optimizing the probability of matching the whole 80-bit digest instead of only the first 48 bits. All these techniques can be described by an MLP model and get the best strategy with a total gain of around 2 to the power of 23.5. In conclusion, this paper gives pre-match attacks on two Kerchak instances. For 3-round Kerchak 256, we introduce a 3-stage model with that. There are more degrees of freedom, and the difficulty of matching the starting state can be solved. Besides, we point out that selecting different Gauss bits will result in different solving time. With these improvements, the complexity of finding a pre-match can be decreased to around 2 to the power of 57.2. For the 4-round Kerchak of B equals to 800, we make improvement through some techniques such as selecting different variables, preparing two candidates for previous message block, using better constant settings as well as the probabilistic digest matching. With the help of MLP model, we finally obtain an attack with complexity of around 2 to the power of 60.9. Thank you. Any questions?
Thank you. Thank you very much. Are there any questions in the room? Yes, there's one question here, please, if someone can. I have a question because your title is very precise. Do you have any hope that your techniques could apply to other variants of Ketching?
We are trying to solve the we're trying to solve the crunchy contest of B equals to 800 sides to one more round with complexity around Gaussian times around 2 to the power of 61. But it is based on internal differential cryptanalysis instead of linear structure. However, some techniques or optimization such as better constant settings or some better linearization that helps us with trying to attack more rounds.
Okay,
Thank you.
Thank you. Yes.
Yeah. Thanks for your presentation. So I found in one page, you said instead of guessing the sum of one column, you can have a better strategy to guess, right? Is this because you find some structures in the sum of the columns, the system to represent the sum of the system? I think it's yeah, this page. Yeah, this and the next page. So you said that instead of guessing the column sums, you guess some bits, right?
Yes.
Is this because I mean, guessing the column sums correspond to some linear equations? Is this because the linear equations is structured and you find something inside it, or it's a general a more efficient strategy?
Maybe this is because if we change this bit to from 0 to 1, the structure keeps linear as well. So we can guess this. We can let this bit be both 1 or 0. However, if we not determine at now and determine and guess it later, so we may first regard it as a variable and later assign value for it. But if we assign we regard the column sum as variable instead of constant, it with very fast diffusion, it will the equation system will be very complex. But if we only let this bit as variable, the equation is still not complex, so we can save it partly save it at
Okay, thank you, Anna. Thank you.
Thanks.
Thank you.
There are no more questions. Okay, so we will thank all the speakers of the session again. Thank you very much.
Thank you.